They offered 2 times. It was 7:30, and another one was probably a mistake. 2:30 a.m.
Who's giving an exam at 2:30 a.m.?
I think HR screwed up,
Oh, okay.
and as a typo, it was probably supposed to be 2:30 p.m.
Gotcha.
But so it's supposed to be, they're giving us 2.5 hours to answer 100 questions, so a minute and a half a question.
Okay, multiple choice.
Yeah, of course. They're lazy. City workers.
I think it's the most of, well, multiple choice is good in the sense that there's no like, no subjectivity in the grading, I guess.
Well, then there's 20 to 25% chance of getting it right.
Yeah. No, but there's no like, with the free response, there's always the argument like, oh, they misinterpreted my answer, or they, they're racist or sexist or something like that. So it makes it great harder. But with multiple choice, there's just 1 of 4, and so,
Or 1 of 5.
yeah.
And but maybe I just want to go. Well, I'll be going home afterwards, so I don't want to take my stuff and leave it in my truck when I'm there
That's fair.
to get broken into, because it is only LA. So
Yeah. No, for sure.
I haven't quite decided if I want to come to campus or not afterwards.
That's fair.
Maybe stay home and work on the project.
Sounds like a good idea. Yeah, you can just kind of watch. I mean, it's a pretty short activity. It's probably the shortest one.
Think about logging. If I stay at home, I was going to log into Zoom.
Yeah, that'll work.
And just if we decided to use one other, we have to pair it up with another random walk.
Exactly. Yeah.
Adam, so
Yep. Mm-hmm.
it was weird. I've tried running the example codes,
Mhm.
and every time I went to with all of them, it said not enough objective constraints.
Not enough objective constraints. What do you mean?
To run the objective function, or just the function at the bottom.
You tried using like MATLABs because the
So
algorithms
I took
themselves.
the code that you uploaded in the example codes.
Yeah.
And I tried running those
Uh-huh.
to look at them.
Uh-huh.
They wouldn't run.
Really?
Yeah.
Huh. Email me the messages that you're getting.
I'll let you.
Yeah.
My laptop.
Okay. Mm-hmm.
Yeah, it was weird one.
Yeah, those codes should be. I mean, all the examples we're covering in class are pretty simple problems, so they should.
Like with the one
run.
that you showed us today, with the function at the bottom.
Yeah.
It takes in x1, 2, and 3, A and B.
Right.
It's like I didn't have enough of those.
Mm.
Where it's kind of saying. I went through and everything's getting pulled in, so.
Oh, that is very strange. I'll take a look. Yeah, show me the
Error.
Yeah, the error.
I've always hated that though.
It can be finicky sometimes.
I just hate coding in general. I told you I started out here in science, right?
Yep. Mm-hmm.
Yeah. And then switched to get away from that. I guess because it's my very first engineering class.
205.
Yeah. With Sanders. It wasn't bad with them. Because we crammed everything into a half a semester.
Uh-huh.
And then the second half we cut it again.
Right. Yeah. He's always told me about his game project.
We did hangman, but he went last.
Yeah, that has negative connotations. A lot of very negative connotations.
Everyone knows what the game is.
Yeah. Mostly for liability, so he doesn't get in trouble.
So this was the hanger on the 17th.
Scary.
That's it up closer.
Still burning.
No, it's done now. And that was what was left that day. It's all. The only thing that's left is the doors and the concrete pillars. Yeah. And when we had the winds, I was kind of a little surprised that the doors didn't get blown over, but not.
Hmm.
But yeah, it's happened with both the trim bells above that. So my dad and I, we like felt Friday,
Mhm.
then we went over to my kid's dad's house afterwards.
Yeah.
So we helped him my grandpa put a battery back in his hot rod. So it was supposed to be a simple, raise the battery and put it, turn it into a 5-hour project.
That's what typically happens.
Well, putting the battery wasn't a problem. It's because the hot rod still didn't start afterwards. So then we went to the starter.
I can see where those go.
I put the starter at 4 or 5, like 3 or 4 times. Wiring issue.
Oh.
Something I missed when you dropped it out initially.
That happens.
Mental note, next time I drop the starter, look at the wires. What? Yeah. Saturday and Sunday. I'm laying on the bed. Oh. The guy was like, oh, and that's the small starter. Because it's a 44.
Yeah.
But he has a small box Chevy.
Oh.
So he got it reliable. The full small box Chevy starter used to weigh 15 pounds.
Yeah.
Now it's a small one that's 5 pounds.
Oh, okay.
Like, well, it's not the heavy one. It's not complaining about the weight. It's laying on that ground.
Yeah. I had to crouch down so much over the break, like painting stuff or like installing something or doing something. Because yeah, my back is killing me for a while too. Bodies are breaking down sooner than later. Oh, wow! I really tore through that insulation.
Yeah, either because it's where it's located is the headers come right off. So this is just a bad normal location, but yeah. Like everyone still on vacation.
Yep. Wish I was.
Another 3 weeks would be nice.
I know, right?
Well, after today, I got.
All right, it's 5:30. Let's go and get started. All right, good evening, everyone. How's everyone doing? Everyone have a good break? Good break? Too short?
Too short.
Too short. Yeah, I know. It's always too short.
Can they make it 3 weeks?
If it was up to me, it would be, but it's not my, I don't make enough money for that. Okay, so we are in the final stages of the class, and so we just have 4 more lecture sessions. So we have 2 this week, 2 next week. My plan for the rest of the semester is that today we're gonna talk about the final project today. So that's kind of the first thing. Thursday we are going to do another ANSYS activity, but it's going to be an optional activity. And so remember, activity 5, which is the last one we did right before Thanksgiving, that is the last assignment that you're going to turn in. Okay. Activity 6 is an optional one. It's quite short. I think it's the shortest activity that I have. But a lot of people like to incorporate it into their final project. And in fact, a lot of people like to incorporate it into their senior design as well. And so I like to go over it just because, you know, it's useful for that. But you don't have to turn anything in for activity 6. Okay. So remember, you guys have to turn in activity 5 this week. And then after that, the only thing that you have to do is just the final project. Okay. Okay. So today we're going to talk about the final project. We're going to talk about kind of a little bit of background information with regards to the activity on Thursday. And then the plan for next week is just to have basically just project work time in classes. So I don't have anything explicitly planned. And so my idea for next week is to just have kind of open office hours for you to kind of work on your final project, ask me questions, look at your ANSYS models, debug any issues, things like that. If you want me to, I do have some additional content that I can go over together with everyone next week. Or we can just do a project work session. So I'll leave it up to you guys. So And so if there's a strong opinion one way or another, just let me know. But I think usually at this point, everyone's pretty tired. So I think having this free work time, project work time is kind of usually that's usually the play for them. Okay. Okay, so that's my plan for the next 2 weeks. Other announcement that I want to make is that I did finish grading your midterm exams, and so that is on Canvas, and so for you to see. The average on the exam was about 35.5 out of 50, so about a 71%. So that's pretty much average. So that's pretty much kind of where that midterm exam is, for the most part historically for the last 4 or 5 times I've taught it. So that's kind of it. So I have the exams today, so I'm going to give them out after the class. Make sure you check the exam. Make sure I added up everything correctly. If you have any questions in terms of why I took off certain points, I'm always happy to kind of talk about that with you guys. Okay. All right. I think that's about it. Any questions I can answer, before we start talking about the final project? Okay. All right. So first thing today, let's talk about the final project. Okay, so there's not much to talk about here because it's almost it's very similar to your midterm project, and so all the parts that are basically the same as your midterm project, I'm just going to go over very quickly. There are a few changes here relative to the midterm project because we did learn some new stuff, and so I want to make sure I go over those differences. But for the most part, it's going to be the same as the midterm project. Okay, the biggest difference in the final project, and I believe I mentioned this a few times in the class, is that instead of being given a geometry for you to work on, you guys can choose your own geometry to work on for the final project. Okay. So typically what I see happen for a lot of the students in this class is that, a lot of you guys are seniors, you guys are in 414 right now. And so a lot of people end up choosing their senior design project geometry or an aspect of the senior design geometry and analyze that as part of their final project. Okay. In fact, a lot of you guys have already done this. And so I've already met with quite a few of you who have already applied answers to a certain part of your final project. And so now, since you already have that analysis done, you can just apply that for the final project here. Okay. But some other ideas to give you in case in case you don't have a final project that's kind of that can be applied to this. Maybe you can analyze a real life structure, and so you can get a CAD file for like maybe the ECS building or something like that. You could look at a historical structure. I always have a couple of those every year. So you can look at kind of the structure of the Eiffel Tower, and so that's the one that someone did before. Maybe like an everyday object that you would find in your house, your car, or the classroom. So kind of very much in a similar vein to the midterm project. So an object like that. Or you could use the final project to design something new. So maybe you're, and so I know that 3D printing is becoming a bigger thing nowadays. And so if you wanted to use this opportunity to kind of test a part that you're thinking about printing, then you can run an analysis on that as well. Okay. Of course, you're not limited to the items on this list. You can choose something else. But of course, if you want to do something else, you can run it by me to before you can get started. Okay. Okay. And so the only requirement that I have for this, for your geometry here is that it should be of appropriate scope. So just kind of keep in mind that we only have about 3 weeks left of the semester, and so you should be able to complete the analysis and complete the report in that time remaining. Okay. For the most part, I won't say no to anything unless I can kind of see from the beginning that it's going to be way too complicated. But if you're unsure about whether what you're considering is an appropriate scope, you can always just ask. Okay. From my experience, the most complicated thing that people tend to do for the final project is that people are almost always a little bit ambitious with the geometry. Okay. So I know probably for a lot of you guys' senior design project, you guys are working on very complex parts with very complicated geometries. You've worked kind of the whole semester on the CAD files. I will tell you right now that for the most part, you're probably gonna have to simplify your CAD files a little bit to work with ANSYS. Either by reducing the number of parts, reducing the complexity, maybe getting rid of some of the finer details, because meshing is going to be probably the biggest challenge you're going to have with a complicated geometry. Okay. And so if you're struggling with the meshing, and so if you really can't really get a mesh, let me know, and then we can kind of brainstorm different ideas on how to simplify the geometry for you. Okay. Okay, but that's the biggest difference with the final project. And so, it's going to be up to you guys to find the geometry, and make sure that you can, run an analysis. Okay. All right. Any questions on the geometry selection for the final project? Okay. All right. So let's go over the requirements. So a lot of these are going to be mostly the same as before. Okay. So just like the midterm project, you're going to need to have an objective. All right. So I think hopefully this should be a little bit easier because you don't have to use your imagination too much. Because if you're doing this for your senior design project, your objective is already there. It's the same objective as your senior design. Okay. But you need to have an objective. Okay. And so I think, from your midterm projects, I think this was kind of the biggest area of improvement that I saw among people in midterm projects was that, there wasn't much in the way of direction in terms of, why you're running your finite elements and kind of what exactly that you're looking for. Okay. So make sure that, for your final project, you really take a moment to think about, what exactly am I trying to, or what kind of information am I trying to obtain about my part, about my structure, and have that kind of direct your analysis. Okay. Okay. Next is going to be background and significance. So that kind of ties into the objective, and so make sure you give me enough background information about the project. Okay. So especially for your senior design projects, and so give me a little bit of background in terms of why this part is being made. What's the purpose of it? Why is it important? If you're part of a legacy team, give me a little bit of history in terms of of the vehicle or device that you're working on, and specifically the part that you want to analyze. Okay. Okay. Next is the validation calculation. So this is a new part. And so if you recall, kind of right before Thanksgiving, we went over lecture notes on verification and validation. And so part of that, in that lecture, we talked about, it's important to, whenever you're running ANSYS, to have something additional to kind of basically do a sanity check for your results. Okay. And so that's what this part is right here. So I want you guys to do an additional hand calculation. It doesn't have to be a hand calculation. Maybe you may have data, from an experiment or a physical test that you run, to basically check the results of your ANSYS simulation. Okay. And so if you're having trouble kind of coming up with what a good validation would be, then let me know. Okay. All right. Next is going to be the finite element modeling methodology. So this is kind of the same as before. So you're going to need to talk about things like the material properties, the meshing, the boundary conditions, all that good stuff. And so you're going to need to talk about those things, justify your decisions, just like the midterm project. Okay. The only new part for this is that you also need to perform a mesh convergence test. All right. I know some of you already did this for the midterm project, but for the midterm project, it wasn't a requirement. But for the final project, it is going to be a requirement. So you are going to have to run a mesh convergence test. And you're going to use that to justify the amount of elements that you're going to use in your mesh. Okay. Okay. So next section is the ANSYS result. And so you are going to present the results of your ANSYS simulation. Okay. And just like before, you're going to need to have 3 different configurations. Okay. And so it's not just going to be one analysis. You're going to have 3 different analyses. Okay. And so for the midterm project, I defined the separate configurations to be, 3 different static boundary condition configurations. Okay. For the final project, you have a little bit more options. So, ever since the midterm project, we went over dynamic analysis. So that was activity 5. And so if you wanted to run a dynamic analysis on your final project, that would count as one of the configurations. Okay. And or you can incorporate activity 6. And so activity 6 is going to be modal analysis, harmonic analysis, right? And so finding like the natural frequencies of your structure. So that would also count as another configuration as well. Okay. And so for the final project, it doesn't have to be 3 static configurations. It can be 1 static, 1 dynamic, and 1 modal analysis. Or you could have 2 static, 1 dynamic, 2 static, 1 modal, or 3 static configurations if you want. Okay. And so I'll leave it up to you guys to kind of decide kind of what's the best way to do that. Okay. But just like all the other finite element decisions that you have to make, you should have to justify whatever analysis that you chose. Okay. And so if you're going to be doing like a finite element analysis of a building, for instance, right? a dynamic analysis of a static building probably doesn't make the most sense, right? And so if you're going to use something like a dynamic analysis, it should be justified based on the objective that you're choosing for your project, okay? Same thing with modal analysis, right? And so, you'll see from activity 6 that modal analysis, is not too difficult to set up. But if you're going to use modal analysis for your final project, there should be a good reason for that, right? And so last year I literally had someone say, like, I did modal analysis because it was the easiest and the quickest to do. So that's not a good reason. So I'm going to give you a 0 on that part if you have that as your reason. So there should be a good reason for using modal analysis, dynamic analysis, for your final project. Okay. The next section here is going to be comparison. And so you're going to compare your ANSYS results to your validation calculation. Ideally, these two should match up with whatever data that you got or whatever you got from the hand calculation. And so you want to kind of compare those results. And then finally, we have the conclusion. Okay. Any questions on the project requirements for the final project? Yeah.
Oh, I was gonna say, if you had like 3 different simulations, you want us to run through like the same format, it's like first set, second set, third set?
Yes. Yeah, so the final report will be formatted the same way, except, for the first one, you said this would be like the first static one, the second one will be, second result, dynamic results, third result, modal, something like that. Yeah.
So for each, if we have 3 different configurations, do we need 3 validation calculations as well?
No, you just need one. And so, exactly, yeah. So what you're going to find out is that the validation calculation is probably going to be a little bit difficult to do. And so you're probably going to choose what most people do is that they choose kind of a subsystem of your geometry, maybe just like a single beam or something like that. And then you do your validation calculation on that. And so you kind of validate just kind of a small part.
So does it even need to match one of our 3 configurations, or we can just validate it and then do
it? Ideally, like the forces should be the same. Like the magnitudes of the forces and the relative geometry should be the same. But it doesn't have to be the whole geometry. It can be kind of just a subpart of the geometry.
What if we switch from static to dynamic? Do we still only need one validation?
Exactly. Yeah. Okay. Yeah. All right. Question in the chat. For the hand calculation validation, do you want us to take a picture and put it on the report as a PNG file? Yes. Yes, and so you should document your hand calculations. And so any work that you do, you should put it in your report. Ideally, I would want you to format it using the equation maker within the word processing thing that you have. But if your handwriting is really neat, then you can take a scan and put that in your report as well. Yeah, it should be legible and professional looking. All right, any other questions on the requirements for the project? Yeah.
Those can have the static for
Yep. You can still, the option is still there for 3 static configurations as well. So if you want to have three different static boundary condition configurations, that's also possible. Yeah. Yeah.
And how flexible do you want the geometry to be? Is it like, do you do like an I-beam, or would you want something more?
I would ideally want something that's more complicated than the midterm project geometries. And so, yeah, it should be more complicated than just a simple I-beam. If you have any questions, or if you think that the project doesn't have enough geometrical complexity, then you can run it by me. Just send me an email with the screenshot, and then we can talk about it. Yeah. Sometimes, if you have a relatively simple geometry, then there are twists that you can run on it. Maybe we can add something to it, or we can, do something to it to make it a bit more complex. And so, yeah, just run it by me just to make sure. Okay, so let's talk about deliverables then for the project. Okay, so there's only one deliverable, and so that's going to be just the final report. And so the due date for the final report is going to be on Monday, December 18th, right? So this is going to be the Monday after finals week, and so it's not the Monday immediately after the last week of class. It's the Monday after that. Okay, and so I push this back as far as I can, just because I know you guys are always really busy with finals week, final exams, other final projects, and things like that. So I'd like to give people kind of the that last weekend after finals week, as well as basically all day on Monday, in order to kind of finish up the report. So it's going to be due at 11:59 p.m. on Monday, December 8th. Okay. But with that said, because I kind of pushed this back so far already, it's really difficult for me to push this back anymore, just because I have to get all the grading done before Christmas. And I have also, all my other classes I need to do the grading for. And then similarly for this class, for all the other classes, I put the due date at Monday, December 18th. And, probably anywhere between 85 and 90% of the projects don't come in until, 11:30 p.m. on Monday night. So I basically only have a Tuesday, Wednesday, Thursday, Friday to grade everything. So it's, I can't really push this back because I need to kind of grade everything before Christmas. Okay. Next, we have the final report components. And so the format of the final report is basically the same. There's a couple extra sections here for the validation calculation. But besides that, it's going to be the same as before. I posted a template for the final report on Canvas, and so you can take a look at that. Okay. All right, teams. And so for the most part, this is going to be an individual project. With that said, I know that there are multiple people in here that are working on the same senior design project. And so I'm not opposed to the idea of teams of 2 working together on a final project. But if you do plan on working in a team, you do need to run it by me, because we need to talk about how we're going to increase kind of the requirements for the project. You need to work in a team, okay? Because if you're going to work on a team, the requirements are going to be different than an individual project. Okay. So for those of you that are working on the same senior design project, what I've seen before in the past is that different people on the same team would maybe work on different components of the final project. Maybe one person will work on one component of the other one, and so then you can submit kind of individual reports. That's fine to me. So if you're going to be working on a team, that's only for the case if you're going to work on the exact same geometry. Okay. Okay. So remember, if you want to work on a team, run it by me, and then there's going to be a max of 2, and so there's going to be no more than 2 working in a team together. Okay. Okay. All right, and so that's it for the final project. And so as you can see, it's mostly similar to the midterm project, just with some added components here based on kind of the new stuff that we've learned ever since the midterm project. Okay. All right, any final questions on the final project? Yeah.
What's the rest of the portion?
So the grad student portion, if you're a grad student, email me, and then we'll talk individually kind of how we're going to add something to your final project. It usually depends on the geometry that you choose, and so usually I ask you to do like an additional analysis. All right, question in chat. Do we need to send you a project proposal before working? So I used to do that. So I used to require everyone send me a proposal. There might be some text in here that references a proposal. I thought I took it all out, but there might still be some reference to that. You don't have to send me a proposal. I think I kind of know what maybe about half of you guys are working on already anyway. So I'm only going to I'm gonna leave it up to you guys. And so you only have to run it by me if you plan on working in a group, or if you have some questions on whether your geometry is appropriate for the final project. So so there's no formal proposal that you have to do. Yeah. Question. So what is the difference between value condition setup and finite element? Okay. Yes. And so so for the final report, actually, let me modify the template a little bit. So that was kind of a relic from last year. So I'm gonna modify the template. I just kind of threw up the same template from last year. But yeah, don't worry about that just yet. So I'll change that on the template. Yeah. Yeah. Thanks for catching that. I've made a couple of changes to the class since last year. Okay. Any final questions on the final project? Yeah.
Changing geometry, like saying loading conditions, but with like say you want to figure out what's the strongest way of doing making a part.
Yep.
You can add these one of your conditions.
Sure. Yeah. And so if you have different geometries that you're testing but the same load, I would count that as 2 different scenarios, and so that would be fine for me. All right, so all the information for the final project is there. So we kind of went very quickly over the specs. but definitely take a read for it yourself. And then as always, just let me know if you have any questions about it. Okay, so so let me go ahead and bring it back here. So let's open up the good old iPad. Okay, and so the topic for today is going to be modal analysis and harmonic analysis. Okay? Okay. So modal analysis is another type of analysis system that you can run within ANSYS, okay? And it's an interesting one because it primarily has to do with vibration, right? So we talked a little bit about vibration when we were talking about dynamic analysis, right? And so when we talked about dynamic analysis, when we introduced the idea of dynamic analysis, what we says that, dynamically, every structure vibrates at a certain frequency, okay? Modal analysis kind of builds on that a little bit, but it kind of simplifies the process of finding that resonant frequency. Okay. Okay. So let me start by saying this. And so up to this point, okay. Up to this point, the primary purpose of all the FEA that we run is mostly to do stress analysis. So kind of that's kind of the flavor that I've chosen for the class, where we run our FEA analysis to compute things like the equivalent stress, and we use that information to determine whether our part is going to fail. Okay. And so stress failure is defined by the fact that if you have an equivalent stress that's greater than the yield strength of a material, so this is equivalent stress, and so if the equivalent stress is greater than the yield strength of the material, then what we've concluded so far is that the material will fail, it'll rupture, it'll break apart, and your structure will be falling apart, and you will be sad, right? That's kind of the premise of a lot of the activities that we've done so far. Okay. Okay. But stress failure is not the only mode of failure for a structure, right? So a structure can fail in a lot of other ways. And in particular, for our purposes for activity 6, we're going to focus on resonant vibrations. All right. So what is resonance? What is resonant vibrations? So every structure has its own natural frequency that it likes to vibrate at, right? So that's kind of that was kind of the subject for activity 5, right? So we rammed our car into a wall, and we saw that the car was kind of vibrating on its own. Okay. Some people call the natural frequency kind of the unforced frequency. And so if you just kind of strike a structure, if you flick it, if you kick it, then it's going to vibrate at that natural frequency. Okay. Some trouble will occur if you actually apply external forcing with the same frequency as a natural frequency. Okay? And so if you cause forcing at the same natural frequency, this is what causes resonance. Okay. And when resonance occurs, visually what you see are these very large amplitude vibrations. And the amplitude of these vibrations kind of they kind of climb higher and higher and higher. Okay? And the problem is, for certain structures, if the amplitude of these vibrations get too large, it can actually be enough to rupture or break the structure, even if the magnitude of the forcing may not be that high, right? If you force a structure enough at its natural frequency, you're going to eventually break it. Okay. Let me give you a couple of examples. Okay. And so this is a party trick that some people could do. I've actually never seen it happen live. I've only seen it happen on YouTube. But it's possible for people to crack a wine glass by just yelling at it or just singing at it. Okay. So a wine glass, maybe looks something like this. Okay. Now you have a person. He's singing at it. It's either a really tiny person or a really large wine glass, whatever you can imagine. Okay. And then if that person sings at a very specific frequency, then that wine glass is going to shatter, right? Okay. And so when people first see this trick, right? And so typically this is done by opera singers. So people have a very large range in their voice and have a very large volume of their voice, right? And so some people think that when you see this, it's the volume of the person's voice that's what cracks the glass, but that's not necessarily the case. Okay. What actually causes glass to break is resonance. And so if the pitch of your voice, right, the pitch being the frequency of the sound that's coming out of your mouth, if that matches the natural frequency of the wine glass, then that can cause resonance enough to break, right? And this could even happen for relatively quiet voices as well. So if you sustain that voice at that pitch for a long enough time, even with a relatively quiet voice, that's going to be enough to shatter the wine glass. Okay. Okay. Let me give you an example that's a little bit more closer to engineering. Okay. So let's talk about building design. Okay. This is especially relevant to California because we get earthquakes here in California. Okay. Okay. So let's say that you're designing kind of a tall building. Okay. Sitting on the ground. One consideration that you have to make, especially in California, is the fact that, your building is going to be subjected to kind of oscillating forces from the ground, okay? Okay. And so the thing with earthquakes is that, when you have earthquakes, you're basically going to have an oscillation or vibration of the ground, right? If that oscillation frequency of the earthquake, if that matches the same natural frequency as the building, then you're in trouble, because then the building is going to start to resonate, and then it's going to basically fall apart. Okay? Okay? So this is actually really relevant for really tall buildings as well. And so if you ever have the chance to step into like one of the very tallest buildings in the world, so I was in one back in 2019. So I took a trip to Taiwan with my friends, and we went to the top of the really tall building there. It's called Taipei 101. If you look in the middle of the building, they have this gigantic counterweight that kind of goes, it almost looks like a big hand of a clock. And the reason that's there is to basically alter the natural frequency of the building, so that when earthquakes do occur, that giant kind of basically pillar that's sticking out from the ground doesn't fall apart from resonance. And so that counterweight is there to kind of modify the natural frequency, offload some of that vibration, so that that building kind of stays upright. Okay. It was very fascinating, and I found that to be the most fascinating part of the building. Whereas, well, now she's my wife, but my girlfriend at the time was taking pictures, and she was getting mad at me why I didn't want to take pictures at the window. Like, I'm reading about the counterweight. I mean, this is really important engineering here, right? Okay, but the kind of the upside to that, well, she married me, so that's all good. So the upside to this is that, natural frequencies and vibrations is a very important part of any kind of structural design. And so it would be really nice if ANSYS or any other program that we have has a way to determine these natural frequencies for us. Okay. All right, and the way that we do this is through a different analysis package within ANSYS called modal analysis, right? And so it's going to be different than static structural, but it's in that same toolbox. Okay? And so what we're going to do on Thursday is we're going to learn how to actually apply this modal analysis, how to interpret the results, and make sure that what we're getting from this actually makes sense. Okay. All right. Any questions on this so far? Okay. All right. So before we jump into kind of what's in answers, let's kind of go over a simple case to kind of build up a little bit of intuition in terms of kind of what to expect in modal analysis. Okay. So let's look at the simplest geometry that we can in terms of vibrations, which is resonance in a string. Okay. So let's consider this geometry. So let's say that we have a string. It's going to be fixed to the wall on one side, The other side is going to be free. This string is going to have a certain length. And so the length is going to be L, right? And the right side, which is not fixed to the wall, is going to be pulled by a force T. Okay? So this T right here is the tension in the string. Okay? L here is the length. Okay, so we can because of the simple geometry, we can derive an equation for the natural frequency of the string. Okay, and that natural frequency is given by the following. Okay, so this Fn here is the natural frequency of the string. Okay. So it's going to be 1 over 2L multiplied by square root of T divided by mu. Okay. So L and T are defined above. So L is the length of the string. T is the tension in the string. This mu is the density of the string, but it's given in terms of, because the string is one dimension, we're going to define the density as a mass per length. Okay. Okay. So I bring this equation up. We're not going to do any explicit calculations with this equation here, but what we're going to do is we're going to analyze kind of the different parts of this equation to kind of build us, kind of give us some intuition in terms of what factors affect the natural frequency of objects in general. Okay. Okay. So the three primary variables in this equation is we have L here. Okay. Its position is going to be very important. So the fact that it's in the denominator is very significant. Okay. We have T and we have mu. Okay. Okay. So let's talk about each of these parameters individually and talk about kind of how they affect the the natural frequency. Okay. Okay. So the first one is the geometry. Okay. And so for a one-dimensional string, we only have one dimension of geometry, which is just the length, right? But we can kind of generalize this to kind of mean, overall volume, cross-sectional area, size of the surfaces, and things like that. Okay. Notice how in the formula here, it's the only parameter here that's not underneath a square root. Okay. And so the fact that the tension and the density there are both under the radical means that geometry here is going to be more influential than the other ones, right? And so a change in the geometry is going to have more effect than a change in the density or the tension. Okay. Okay, 2. All right, so the second group of factors that affect the natural frequency of objects is going to be its material properties. So these are going to be things like the density, obviously. Okay. The overall stiffness of the geometry, so things like its Young's modulus. Okay. The Poisson's ratio has an effect, although it's a little bit less of an effect. But basically, just whatever material it's made out of is going to affect its natural frequency. Okay. And what's interesting is that each of these properties here have a different effect on the natural frequency. Okay. And so explicitly in this equation right here, we can see the density plays a role kind of in the same vein as the geometry, right? And so increasing the density, right, because it's in the denominator, increasing the density will actually lower the natural frequency, okay? But that's not the same case for the stiffness. And so the stiffness is actually kind of more similar to the tension, okay? Okay. And so the last factor here that can affect the natural frequency of a structure. So usually when people think natural frequency, they usually think of the first 2 things. Okay. Third factor is usually not talked about too much, but that factor I call that pre-stress. Okay. Okay. It's like pre-gaming, but pre-stress. It's stress that you have about having stress. Okay. Okay, but in this setting, pre-stress basically means as any kind of residual internal stresses that are in the structure before the vibration occurs. Okay. Okay. And so if you have any static loads that are being applied on the structure, that's going to affect your natural frequency. Okay. And we'll see that in activity 6. And so in activity 6, we're going to compare. So we're going to have 2 cases where one, we compute the natural frequency without any external loading, without any static loading. And then we compute the natural frequency after you apply a static load. And you're going to see that it actually changes a little bit, okay? Because the state of stress within a structure does change its vibration properties. Okay. Okay. So keep all these things in mind. And so, the natural frequency of one structure can be different than the other, usually based on these 3 factors. Okay. All right. Any questions on this so far? Okay. All right. So let's talk about harmonic modes. Okay.
My face is swollen. So can I just-
Oh.
Do you have one or not?
Okay, so harmonic modes. And so the thing with harmonic modes is that there's more than one natural frequency for a structure, right? Usually when we think of resonance and we think of vibration, we think of just the first harmonic mode. So this equation right here is the first one. Okay. But in reality, resonance can occur at different frequencies. And this is actually especially relevant in multiple dimensions. Okay. And what's interesting is that if you cause resonance at these different frequencies, each one of them is going to have a different deformation shape. Okay. So I guess first of all, we call all the different frequencies where resonance occurs. Okay. So all the different frequencies where the resonance occurs are the harmonic modes, okay? And you can kind of visually tell kind of which harmonic mode that you have because they're going to look different, okay? Okay. Okay, so for example, let's look at the different harmonic modes for a string. Okay, so the first harmonic mode, okay, so the first harmonic mode for a string will look like this. Okay, so it looks like a jump rope. Okay, okay. Next, we have the second harmonic mode. Okay, so it looks like a sine wave. And then let's do one more just for good measure. Okay, so third harmonic mode, something like that. Okay. All right. So each of these harmonic modes corresponds to a different frequency of excitation. Okay. So typically speaking, you know, for the most part, you only view the smallest harmonic mode or the first harmonic mode, okay? Because the other harmonic modes are they're just kind of a little bit more difficult to get to, okay? In 1D, we actually kind of have this unique property where each higher order mode, second mode, third mode, fourth mode, and so on, those are all integer multiples of the first harmonic mode, okay? So F2 is actually 2 times F1, where F1 is the first harmonic mode of the string, okay? And then F3 is 3F1, okay? But that's only in 1D, okay? And so in multiple dimensions, you're going to have different harmonic modes, but they're not going to be integer multiples of each other. Okay. And so the primary reason for this, the primary reason why you're not going to have integer multiples is that you're going to have different amounts of resonance or different resonant frequencies in each dimension of the structure. For instance, if you have let's say kind of just a triangular block here, right? You may have one frequency. Maybe the smallest harmonic mode is going to be vibrations in that direction. Okay. But then maybe you have another harmonic in this direction. So this is F2. Okay. Where in this case, F1 and F2 are not integer multiples of each other. They are kind of just separate numbers. Okay. All right. So that's just a little bit of background on kind of modal analysis, right? Basically, every structure has its own natural frequencies. The smallest natural frequency, we call that the first harmonic mode. But then there are higher frequencies that can also cause resonance, but they cause different vibration shapes and they're in different directions. Okay. All right, so our objective, so what we want to find out in ANSYS here is we want to find out for a given geometry, and for our case too, for a given kind of a boundary condition setup, what are the resonant frequencies and what do the vibrations look like at those frequencies? Okay. All right, any questions on this so far? Okay. All right, and so to answer these questions, we can run a modal analysis in ANSYS, and that's gonna answer everything. Okay, and so for the most part, I'm gonna leave most of this analysis to Thursday in the activity, but I did want to mention a few kind of important factors, just because it's going to be important to know kind of before we actually run the harmonic or the modal analysis. Let's talk about modal analysis in ANSYS. Okay. Right. So compared to dynamic analysis, even compared to static structural analysis, modal analysis is relatively simple. There's really not much to it. So the only requirements that you have is that you have a geometry first of all. It is mesh, and so you need to provide a mesh for it. You can provide boundary conditions, but the only boundary condition that's strictly needed is actually a fixed support. So you actually don't even need to apply any loads. Okay. And so after running the modal analysis, ANSYS will give you a list of resonant frequencies for that geometry. Okay. Right, so that's the bare minimum of what you need for a modal analysis. So you just need a mesh, and you need at least one fixed support, because you need to prevent rigid body motion. Okay, and if you provide both those things, then you are able to get a list of resonant frequencies. Okay, you can add a load, and so it's not illegal to add a load. Okay. And doing so will generally change the resonant frequencies, not too much, but it will change them. Okay. Um, the the reason it's going to change is because it's by adding loads, you're changing the state of stress within the structure. So you're essentially adding pre-stress to the modal analysis. Okay. Okay. So with that in mind, the requirements for a modal analysis are actually not all that different from a static structural. And so one convenient way that you can set this up, and this is kind of a convenient setup for your final project as well, is that you can link a modal analysis directly to a static structural analysis. So that it uses the same mesh, same boundary conditions, and so you can just run it just straight from there. Okay. So a little bit of a nice, convenient way to do that. Okay. All right. And so the other thing that modal analysis will give you, and this is the part that's a little bit more exciting, because you'll see on Thursday that just getting a list of frequencies is kind of boring. Okay, it's just a list of numbers. But from that list of resonant frequencies, you can actually view what the harmonic modes actually look like for those frequencies. Okay. And so, for example, so let's say that we ran modal analysis on a string, right? So our 1D string, I mean, I already drew them, so we know what the three harmonic modes look like. Okay. We have F1. We know F1 looks like this. Okay. We have F2. F2 looks like this. And we have F3. F3 looks like this. Okay. And so you can have ANSYS display these for you. And ANSYS is going to show you in basically in the same form as a deformation plot. Okay. Okay. But you have to be a little bit careful here because, you know, the thing to remember in modal analysis is that you're not actually applying any external vibration loads. Okay. You could apply static loads, right? That's fine, but you're not actually applying any kind of external vibration. So you're not applying any earthquakes. Okay. And so it's very easy and you know, and even though I'm saying this, you know, people will ask this on Thursday, to look at these plots for the modes and think that these are actual deformation plots, right? These are not actual deformation plots. Okay. So I'm going to underline not 3 times because it's an important point. Okay. And so I think what the modal analysis kind of leads people to believe is that if you force a structure at that particular frequency, then you're going to get a deformation plot that looks exactly like a harmonic mode. Okay, that's not necessarily true because the amount of resonance or the actual resonant mode that you get also depends on the magnitude of the forcing as well. Okay. Okay. Let me give you an example. Right. So let's look at our building again. Okay. Okay, so let's say that our earthquake here is subjected to an earthquake, right? Our building here is subjected to an earthquake. Okay. If the earthquake is really small, right? So in California, we get tiny earthquakes all the time. And so but for the most part, you know, we don't really feel the tiny earthquakes here in California, right? But if you had a bigger earthquake, that's a lot more. You feel that a lot more, right? And so even if that tiny earthquake, even if that was vibrating at the same natural frequency of a building, you know, that tiny earthquake usually is not enough to topple a building just by itself, right? Because the building itself kind of has a lot of natural damping and a lot of kind of safety factors that kind of go into it. Okay. But a big earthquake will almost surely topple the building, right? So the actual response or the actual deformation depends on the magnitude of the forcing itself. Okay. Okay. Same thing for the wine glass example that I gave you at the beginning of class today, right? Even though even though I mentioned it is possible for a very soft, very quiet voice to shatter a wine glass, it's going to take a lot longer to do that because it has to sustain that resonance for a longer period of time. But if you have a very loud voice, that basically forces the wine glass at its resonant frequency, it's going to break a lot faster because the magnitude of that forcing is much greater. Okay. So I'm bringing this up because in modal analysis, we're not actually applying any kind of external oscillating force, okay? We may have applied a static force, but the static force doesn't cause resonance because it's just static, right? And so all that we're viewing, and so the only reason ANSYS will show you these plots is to give you a sense of the shape of the mode. Okay. And so, when you view these deformation modes, and I'll remind you again on Thursday as well, it's going to show you units as if it were real deformation, but it's not. It's not real deformation. It's just there just to give you a sense of the shape. Okay. Okay. All right, and you'll see that for three-dimensional objects, the shape of the modes are actually quite interesting. But I'm going to caution you not to take the magnitudes of that plot seriously. Okay. If you actually did want to cause resonance, ANSYS does have another tool in it called harmonic response. And so in harmonic response, in that mode, you can actually apply an oscillating forcing. And you can actually observe just how much resonance and just how much deformation you actually get from that. But in just modal analysis, we're just viewing the shapes. We're not actually applying any kind of oscillating. Okay. All right. Any final questions on this? Yeah.
So, I think you kind of think the other mode, like if you have a rocket, is there a way to determine like what kind of natural frequencies the experience from like an impulse of a rocket?
Yeah. In that case, that's actually a pretty complicated question because then you kind of have to simulate kind of the pulse itself. And so that's kind of more that kind of links together like fluid mechanics together with the structure. So you have to kind of simulate fluid mechanics of the pulse and kind of what frequency that would kind of impart onto the structure from there. So yeah, that's a pretty complicated analysis, but yeah, you'd have to run CFD. So it's possible. People in NASA do it all the time, but it's definitely pretty complicated. There's a lot involved in that. All right, any other questions? Okay, I have your exams, so you guys can come up and pick them up. We send it up on top. Yeah.
Both right on.
I think you were the first to turn it on both ones. So remember, the average on the exam is 35.5, so go ahead and pick it up. If you're not here in class today, if you're on Zoom, I'll bring the exams back on Thursday so you can pick it up then. But besides that, thank you guys for coming today. I hope you guys enjoy the rest of your day, and I will see you on Thursday for our last activity.
Have a nice day, Professor.
Yeah.
So I was in, brother, my cousin and I were in La Mirada at the golf course.
Yeah.
And we're in the parking lot talking, just actually shut the lights off.
Oh my gosh. Oh, wow.
And my brother and I were getting in the car, we just watched the whole parking lot.
Oh my gosh.
That was weird.
That's crazy.
My cousin was backing up, he thought he had something over, no, that was an earthquake.
That's crazy.
So, from, since the last time I talked to you with like the model and Nancy, I was able to figure out things being,
Okay.
I even found a way to like not have to be taking the contribution number.
Okay, great.
Nothing basically like touch there and like it'll transfer all the connections over.
Oh, great. Oh, that's awesome.
Yeah, the only other thing is that like, you know, this at the bottom of the tree, there's solutions, you right click the things that you want.
Yeah.
I'm able to put the information on there easily, but for whatever reason, it like, basically, I wanted to see, yeah, but when I tried to open up the model, it like, said that like I was using a future version, so it's like,
It might have been just it might have been, yeah, it might have been well, yeah, it just has that annoying thing, where you can't open up, feature versions. So I think the ones we have in class here are 20.
so when I right clicked on it.
Yeah.
They didn't show the same option. That's like,
Yeah, and it's they're beam, so.
So what should I put instead for complete stretch?
So if you look under beam results there should be something in there called like the beam forces or the beam stress. And so it should- Yeah, something like that, it's just like forces, like compressive forces or something like that. That's probably what you're looking for. But under beam, might be under, yeah, beam, either beam results or beam, one of these. That's the only one I have for 10. I have 454. Oh, you have a score on campus?
Yeah.
Okay. What's your name? Okay. Okay. MJ, if it's fairly quick, we can discuss it right now, but I just have to be back in my office by 7. But if you want more time, we can discuss after class on Thursday. Okay. Okay, let's, if it's not urgent, then let's meet on, let's talk on Thursday then, after class. If it's urgent, then I think I have some time, maybe after 8 o'clock today. I think that's when I'll probably be done. But yeah, if not, then we can talk on Thursday. Okay.